hear? Okay. I still have to look over the exam a little bit longer. Hey, fellas, let's get started here. Got a lot of stuff to cover. So I need to look over the exam a little bit further. There might be some discrepancies. There might be some points that I can award back. But right now, looking at all of the midterm exams from yesterday, the average is a 68%. Yes. So I just need to look over a little bit more, see if I can't be a little bit more lenient. Looking at some of the data, if a question was written unfairly or if it could be interpreted a different way. I do want the exam to be fair. So I'm just going to look over it a little bit more, but I should publish the your grades later this week, probably tomorrow, but it might be some time before I can actually publish the actual results, like the actual questions. But I will post those questions by the final, right? So there's that. So 2 more chapters to cover before the final. The last lecture day, I do want to spend doing review because our final exam is cumulative. I plan on having a review session on reading day. So reading day is on Tuesday, and I think our reading day is the day between the last day of classes, which is a Monday, and the first day of finals, which is a Wednesday. Yeah, you look confused, so I'm just clarifying. Oh, is that what you're just, okay, that's just your face. Okay, great. Okay, so Tuesday is reading day. I'll have a review session then. And then I think our final exam is on Wednesday. Yeah, okay, all right. So we left off talking about chemical equilibria, Le Chatelier's principle. These were the topics that you really needed to answer the questions and come up with conclusions in the LCP lab that Tuesday folks did. Thursday folks will have a little bit more information under their belt. So the idea of Le Chatelier's principle is looking at systems that are already at equilibria. So we could just have, some type of equilibrium where we have this new type of double-sided arrow. That's a new kind of arrow that I introduced in this chapter where both sides of the reaction exists at the same time. The ratio between A and B tells us our equilibrium constant, big K. All right. And so based upon, if we already have a reaction that's at chemical equilibrium, we can make disruptions to this chemical equilibria. We might have like 3 B atoms and 2 A atoms or something present at equilibrium. Well, if we change the concentrations of one of the species, we can disrupt that equilibrium. But the reaction needs to adjust itself to get back to that ratio, back to that chemical equilibria K. So with concentration, I usually like to just think of this like a seesaw, that at equilibrium where we have like our balanced seesaw. But if we add a product, we kind of push down on one side of the seesaw. And in order to get it back to equilibrium, back to like equal sides, we have to produce more products. So if you add a reactant, the reaction shifts to products. And then the opposite is true too. If you add product to a system already at equilibrium, so if we add B, the reaction has to shift to A to make up for that addition to get to K equilibrium. You can also remove reactant, and it's the same idea. If you remove reactant, the reaction will shift to the left to make up for it. If you remove product, same idea. You shift to the other side. So that's just kind of using qualitative thinking to predict shifts in reactions. That's essentially Le Chatelier's principle. We also looked at changes in pressure by expansion or compression of volume of containers. Same idea. We want to look at relative gas particles on either side to think about how a chemical equilibrium will establish itself. The last point here is looking at temperature. Changing temperature of chemical equilibria. And I think that's kind of the cool way or one of the cool examples of looking at shifts. And so we talked about the quick and dirty way to predict shift when it comes to changing temperature. And I told you just treat heat as a product or a reactant, depending if it's endothermic or exothermic. And so, we just treat it like increasing or decreasing concentration of a reactant or product, that will get you the correct direction of the shift. But I'll explain it a little bit further in the next slides. So in this exothermic reaction, heat is a product. So if we heat up the reaction, we're adding a product, the reaction shifts to the reactant side. And that matches exactly the observations we make if you were to do this in lab. For this endothermic reaction, potassium chloride, this is endothermic, so heat is a reactant. If you heat it up, calcium chloride becomes more soluble at higher temperatures. So again, treating heat as a product or reactant is the quick and dirty way to do it. The real reason why reactions shift when you change the temperature, all right, when you change the temperature, is not because heat is a product or reactant. It actually has to do with kinetics and the Arrhenius equation. Oh, okay, one last thing. So the example that I showed in class in a demo last week was looking at a reaction at equilibria. I put it in a hot water bath and then the same reaction in a cold water bath. And you saw different colors present in the hot water bath versus cold water bath. So based upon the colors, you could tell where triangle had to be in order to see those colors, to see that observation. So just based upon these colors, and I think you do this exact thing in lab, is that you look at a chemical equilibria, both in a cold and hot water bath, and you need to figure out where do you put triangle to make those observations true. So based upon this, I like to look at the hot water bath, and I think, okay, if I add triangle, it becomes yellow. So that means triangle needs to be on the product side, because if I add heat, the reaction becomes yellow, and that matches our observation. So just based upon these observations, we can say that this reaction is exothermic. Again, treating it as just a product or a reactant gets us the correct, I guess, conclusion here. And then we saw again for this cobalt system, which was pretty cool. And then you do it again. Is the system you study, what is it? Is it chromium, cobalt? People who just did it? Because it was a different set of colors, wasn't it? It was copper. Okay, so it was copper. So that was like a green and light blue, but same idea. Okay, here are my opinions. It's okay. You get to reuse that one. Okay, that's fine. Yes. Okay, thank you. No problem. All right, so treat triangle as a product or reactant. That's the quick and dirty way. The real way to treat shifting equilibria with temperature is we're actually changing the value of K, big K. And the reason, right, the reason that we're changing K is we want to remind ourselves that K, how we get equilibrium constant is actually from rearranging the rate laws for the forward and reverse reaction. Remember when we talk about K, usually we say it's products over reactants, concentration of products over reactants. We can also say that big K is the ratio of the forward rate constant over the reverse rate constant. We talked about this at the very, very beginning of this chapter. All right, so forward rate constant, reverse rate constant is the same thing as our rate constant. So let's recall from, was this last chapter in the Arrhenius equation? Yeah, you were just assessed on this. All right. What was the trend with rate constant? Reactions go faster when temperature is hot, right? K increases when temperature increases. How is K related to activation energy for a reaction? Typically, reactions go fast if activation energy is small. Yes, small hill, you go over really fast. So we want, small activation energies. For fast rate constants. All right, so when we did the 2-point Arrhenius equation, natural log, like K2 over K1 equals EA over R, temperatures, all that. What was the idea there, or like the small detail, that reactions that have what kind of activation energies are sensitive to temperature changes? You remember that? What kind of activation energies? Big activation energies are sensitive to temperature changes, or small activation energies are sensitive to temperature changes. You remember? It's actually large activation energies that are sensitive to, oh, it's written right there. It's written right there. Large activation energies are sensitive to temperature changes. K changes more. Remember my analogy, my weight training analogy? right? That when I was in weight training in high school, my K was already real small. So as time went on and I improved, my percentage I improved was a lot more than the folks that were already benching 200 pounds at the beginning of the year. It was much harder. They were already going fast. So if you give them a little bit more temperature, a little bit more kinetic energy, they're already going fast. So they're just going to go a little bit faster versus a reaction that's already going slow. It's already going slow. If you give that slow reaction a little bit more energy, a little bit more kinetic energy, it's going to use that more comprehensively and go much faster. So that's why large activation energies are more sensitive to temperature changes. Okay, so keep that in mind. That's the importance phrase here. So let's look at this endothermic reaction. Endothermic means that the reactants are more stable than the products. So when we increase the temperature of this chemical equilibrium, so it's both going backwards and forwards, what happens to K forward, the rate constant for the forward reaction? Does it increase? When we increase the temperature, does K forward increase? Yes, K always increases when temperature increases, always. What about the reverse reaction? Does it increase too? Yes, it does. But how does it increase? Does it increase more? Does it increase less? It increases less than K forward. Why? Because its activation energy is smaller. The reverse reaction is already going fast. All right, so it's going to go up less. So how does K, big K, which is the ratio between the forward and the reverse rate constants, how does that change? K becomes larger. Yes, larger. Becomes larger. All right, and that's because both the numerator and the denominator increase, but the denominator increases less. So that's why K, big K, becomes a larger value. So if K, the value of K becomes larger, and remember that K is equal to products over reactants, what kind of shift should we see? If K increases, we should make more what? Products or reactants? Products. And is that consistent with Le Chatelier? When we heat up an endothermic reaction, right? We heat up an endothermic reaction, what kind of shift should we see? It should shift to the products. So that is consistent with K, our use of the Arrhenius equation, right? So this is the real reason why equilibria shifts when we change the temperature. So let's do the same thing for an exothermic reaction. All right, so here's an exothermic reaction. The idea here is that, if you increase temperature, K always changes, but depending on your activation energy, if you have already a large activation energy, a slow rate constant, temperature is going to change that K more. So let's think about this. Here's our exothermic reaction. Forward and reverse are happening. So let's think about it. How does the forward reaction change when we increase the temperature? Does it increase? Yes, it increases. K always increases. What about the reverse reaction? Does the reverse reaction rate constant increase as well? Yes, but it increases, but more. Yeah, it increases more. It increases more because the hill to go in the reverse direction is bigger. All right, so more because larger activation energy. The reverse reaction is already going slow, so it's going to be more sensitive to temperature changes. And so how does that change K? Big K. K is actually going to decrease. Yeah, so if K decreases, we should see more reactants form, right? Because if K gets smaller, the value gets smaller, you can think, okay, the numerator gets smaller or the denominator gets bigger. Reactants are in the denominator, so you're going to make more reactants. Is that consistent with Le Chatelier's principle? When we heat up an exothermic reaction, exothermic reaction means we have heat or triangle on what side? On the product side. So you tell me, when you heat up an exothermic reaction, which way should it shift? To the reactant side. And is that consistent with what we just said? Yes, it is. Isn't that gross? Yeah. So the real reason why chemical equilibria shifts for temperature changes is because we're actually changing the value of K. Though Again, if you just treat heat like a product or reactant, you get the same answer in terms of the shift. But it all has to do with kinetics. All right, so let's review Le Chatelier's principle with our favorite evil reaction, our synthesis of ammonia. So let's put all of these ideas together using Le Chatelier's principle and thinking, okay, we have this ammonia reaction already at equilibrium. What's going to change? How does this reaction equilibrium adjust itself with these small deviations, with these disruptions? So this reaction is currently at equilibrium. So if we increase N2 concentration initially, how will the reaction try to accommodate that? Which shift will you see? The reaction will shift to the products or the reactants? Products, yes, because when you add N2, you're adding a reactant. Okay, so just think of that seesaw analogy. All right, what if we decrease H2 concentration? Which way does it go? The other way. I'm not good with my lefts and rights. It goes to the reactant side because you're removing a reactant. So the equilibrium is going to try to fill in that reactant that you removed, essentially. All right, NH3, which is a base, is neutralized with an acid such as HCl. What's going to happen? So if you neutralize a base, you're essentially removing a product. So if I just change this question to remove a product, which way will the reaction shift? To the product side. So by neutralizing that product, I'm essentially removing it. So it's the same thing as me just saying you removed NH3, all right? Okay, but just through a neutralization reaction. All right, what if the pressure of the reaction doubles? So it looks like we're increasing the total pressure of our system by compressing the container. Which way will the reaction shift? We increase the pressure. The reaction's going to shift. It's going to want to relieve that increase in pressure. So what side of the reaction is going to be favored, products or reactants? It's going to shift to the product side because there's less moles of gas on that side. Moles of gas. And that's how it's going to relieve that pressure. But what if the opposite happens? What if we expand the volume of the container, thus, I guess, reducing the total pressure of the system? If we reduce the total pressure of the system, the equilibrium wants to kind of fill in that void that you just made. So it's going to shift to the side with more moles of gas to make up for it, more moles. Okay. All right, what if I heat the vessel? Which way is it going to shift? Where does your triangle live? Did I tell you where the triangle goes? I did tell you. Which way does it shift when I heat this reaction? To the reactant side. So the small piece of information that you might have missed, glossed over, is I said that this is an exothermic process. So that means that triangle is a product. So if I add more heat to this reaction, it's going to shift to the reactant side, right? That the equilibrium will shift to the reactant side. Versus a reaction vessel is cooled, it'll just the opposite is true. You're removing heat, you're removing triangle, so the reaction will shift to the product side. All right. So feel good with Le Chatelier. It's all qualitative. It's all qualitative, but you can look at it numerically as well and actually calculate Q and understand, okay, what kind of shifts need to happen. So Q becomes K, and that means shifting reactant and product. K is always products over reactants. So if you think about that qualitatively, you'll be good. All right, so that's Le Chatelier's principle. Now you basically know everything to complete the lab. All right, so just look at the chemical shifts that are happening in lab, those observations, and relate that to Le Chatelier's principle. All right, so before we move on to KSP stuff, we're gonna go back to slide 9, and we're gonna bring back out our calculators. All right, so we're gonna go back to slide 9 because I skipped over this earlier. Okay, slide 9, okay. So more towards the beginning of the chapter, I described to you what big K is, equilibrium constant is. Generally, It's the concentration of products over reactants when you have a system that is at equilibrium. Equilibrium means that the forward rate of the reaction equals the reverse rate of the reaction. So what we observe is no net change in concentrations of stuff over time. Instead, what we're looking at is just this constant concentrations of products and reactants. The forward and reverse reactions are happening. It's just we don't see a net change. And so this is an intensive property of a chemical reaction. And so, depending on what system you are studying, you can have a different K value that tells you the ratio of products over reactants that are present at equilibrium at that specific temperature. We can also relate it to rate constants too, that we talked about. Kf, small k, F over reverse is also equal to K for elementary reactions. So just based upon like numerically what K is, if K is a really big number, remember it's products over reactants, you have a lot of products at equilibrium. If K is really big, right? If K was like 100, you have like 100 times more products than reactants, right? Because 100 is the same as like 100 over 1 products of reactants, versus if K is small, right? If K is like 1 times 10 to the negative 4, that means you have like a real big number on the denominator. You have a lot of reactants present at equilibrium. This is really helpful for us to predict shifts when it comes to like Le Chatelier's principle and for calculations, because we're going to have to do some approximations here. All right. So let's do some other manipulations of K and understand what K is. Remember, K is products over reactants. So let's write the K expressions for these two equilibria. What is the K expression? Let's say Kc, so concentrations. What is the Kc of this first reaction? It's going to be concentration of C over concentration of A times concentration of B. This is products over reactants. Make sure you keep the coefficients, but everything's a 1, so coefficients become subscripts, or sorry, superscripts, so we're good there. All right, so that's the first one. What is the K expression for the second reaction? It's products over reactants. So it looks like it's just going to be A times B over concentration of C. Great. How is reaction 1 related to reaction 2? They're reverse reactions of one another. How is K? I'm going to call this K1 and this is K2. How are those two expressions related to one another? They're inverses of each other. So it looks like if we flip a reaction, if we reverse a reaction, how do we have to change the K value? We take it to the -1. Does that sound kind of familiar? Sort of familiar? Okay, let's do another one. So that's if we reverse a reaction. What if we take the sum of a reaction? So let's look at these two reactions, A to B. So that means that Kc for this first reaction is just going to be B over C, or no, B over A. Come on, B over A. Okay, what if we do B to C? The equilibrium constant is just going to be C over B, right? Okay, so what if we added these two reactions together, reaction 1 and 2? So let's look at that over here. Pretend this was like kinetics or something, and these are two steps to your mechanism. What is the overall reaction? You turn A into B, and then B gets consumed into C. What is the sum of those two reactions? You have A being converted to C. Yeah, so B looks like it's an intermediate. All right, so let's write the new rate constant for that reaction. It's going to be concentration of C over concentration of A. All right, so we have 3 different Ks, K1, K2, the new K3 for the sum of the reactions. So how are these equilibrium constants related to one another? Yeah, by multiplication. So it looks like this new K3 value is K1 times K2. And we see that B term cancels out. Because B is an intermediate, it doesn't show up in the overall reaction. It also doesn't show up in the rate the equilibrium constant. All right, so I'm hoping that this sounds familiar, just a little bit different, right? This is like Hess's law. It's just you have to manipulate it a little bit differently. So by adding two reactions, instead of adding the Ks, we multiply the Ks. That's basically it. All right. So these are the ways we can manipulate K expressions to get a new K expression for a new reaction. All right. So if I tell you that the K for this reaction is 0.2, how could we manipulate that K value to get this second reaction? We have to do what? How do we manipulate that? Multiply by 2. That's what we do to the reaction. So do I multiply the K value by 2? No, I'm actually going to take that K value. Oh my gosh, they're so freaking annoying. But then it's going to get hot. All right, so this new K value for that manipulated reaction is going to be 0.212 squared. We doubled the reaction. Not in Hess's law, we would have doubled enthalpy. But with Ks instead, we just turn all of those multiplications to exponents instead. All right. Oh, and so here are the general rules. You can see it down there. But let's just do this last one. What if we wanted to turn this first reaction and figure out what is the K expression for this third reaction? Yeah. Am I reversing? Oh, I am reversing it. That's why you're making faces. Yeah. Okay. So if I reverse it, what do I do to K? I inverse it, which is what operation? To the -1. Yes. All right. Very good. It's because they're so noisy. My brain fog. So flip. Yes. If we flip it, we have to take it to the -1. Great. All right. So now what manipulation is the pink line? Now I flip it, or no, now I multiply by 2. Great. Now I multiply by 2. So if I double the reaction, do I double K? No, I have to take the square of K. So the new K for this reaction is going to be 0.212 squared because I doubled the reaction. So if you think Hess's law, but you just use those manipulations as exponents, that's how you get it, right? And so here are the general rules. Reverse a reaction, it becomes the exponent, so to the -1. If you double a reaction, to the 2. If you triple a reaction, to the 3. If you have a reaction, you take the exponent to the 1/2, which is the same thing as a square root. Okay. What if I take a reaction and I reduce it by a third? What am I going to do? What am I going to do to K? Take the cube root, so 1/3. Okay. So to the exponent 1/3. What if I flip a reaction? So I'm going to flip a reaction and multiply it by 4. What exponent am I going to take it to? The 4th? The -4th, because I flip it. All right, so I flip it. So that's the -1. And then if it's times 4, I do to the -4. Good? All right, so let's put that practice and manipulate one. All right, so here, and again, if you just think Hess's law, you're good here. This is my target reaction. I want to figure out what is the Kc for this. It's the same exact, idea. We want to figure out how can I use these given reactions to get that target reaction. So I'm going to just focus on things one at a time. All right, NOBR, that's a product in the first given reaction, and it's a product in the target reaction. So I'm just going to keep this as is. I'm actually not going to do anything to it, right? Because it looks like I have NOBR in the right place and in the right number. But now if I look at the other things, what do I need to do? What do I need to do? It looks like I need to get this N2 on the other side. If I see I have N2 as a reactant, but I have N2 as a product in that second reaction. So what do I have to do to that second reaction? I need to flip it. Yeah, so let's flip it. All right, is it in the right number though? Yes, so it looks like I just have to flip it. So I'll just rewrite that. So N2 plus O2 gives us 2NO. And so if so I'm just going to quick cross that out there. If we add up these two reactions, reaction 1 and reaction 2 that I've already flipped, you can see things cancel out where the NOs cancel out. All right, those NOs cancel out. So we get that the full reaction is N2 plus O2 plus Br2 gives us 2NOBr. And that is my target reaction. So those manipulations that we did, we need to propagate to those K expressions. So Kc for that first reaction stays as is, but the second reaction, because we flipped it, I have to take that Kc value and take it to the -1. All right. So my answer here, my answer for my target reaction, that K value is equal to 2 times 2.1 times 10 to the 30 to the -1. So whatever that is in your calculator and sum it. Right. So instead of adding those Ks, we're just multiplying them all together. Right. But it's the same strategy as Hess's law. It's just the manipulations are exponents instead. Good. So fun. So is this reaction based upon our answer? All right, this was our target reaction. So look at that target reaction. What's more present at equilibrium? Products or reactants? What's more present at equilibrium? Reactants, how'd you get that? K is real small. So that means you have a really big number in the denominator. That's where the reactants live. So you don't actually make a lot of NOBr. Okay, right? So the numbers have meaning, and I want you to think about that. All right, this is the hardest part of 1220. At least they think it's hard. So we'll see what you guys think. All right, they've been learning about this for like 2 months, right? And we're gonna learn about it in 1 week. All right, so who's heard of ice tables before? Ice tables? Matt, put your hand down. Okay, all right. Ice table. It's kind of like a BCA table, before, change, after, how we did stoichiometry, but it's a little bit different. Ice tables, they're applied specifically to things that are chemical equilibria. All right, and that's because of one of the definitions here. Ice stands for initial, change, E stands for equilibria. So we use ice tables when talking about chemical equilibria. BCA tables, do you remember that? It's been eons. BCA, do you remember what that stands for? Before, change, after. When you set up a BCA table and an ice table, it's actually very similar how you set it up, but they're applied to different reactions. BCA tables are applied to reactions that go to completion, reactions that have like full-blown like go arrows, versus chemical equilibrium, we have the double-sided arrow, right? So this is a BCA table. Use that for BCA table chapter, I don't remember, 4. We will go over it for the final exam review. But now we're talking about chemical equilibria. This is where we use ice tables. It's different, but it's similar to BCA. All right. So if we remember looking back at some of our examples, like our ammonia example, I told you, okay, here's the concentration of your products and your reactants. Tell me what K is. So in those examples, I already gave you equilibrium concentrations. So here's the problem. What if I don't give you equilibrium concentrations? What if I give you initial concentrations? That's how we complicate things, but we can still solve for it. And I'll show you how we do that. And we use the ice table to do that, where initial means initial conditions. C stands for change to get to equilibrium. E stands for equilibrium. The trick is, for ice tables and chemical equilibria, is that whatever values you have in your equilibrium line in your ice table, that's what goes into K, into your K expression. What's in that box, I want you to say 10 times before you go to bed tonight. The E line goes into K. The E line goes into K, your K expression. All right. Okay, let's do an example. This example does not have a solution. I just want to show you how we do a ice table. And again, it's very similar to a BCA table. So let's pretend we have this crazy reaction, A combining with 2 B's, equilibrium to give 2 D's and 3 E's. And let's say I tell you, you start with A and B, and I'm asking what's present at equilibrium. So the change line is the same as we did for BCA tables. This is dictated by stoichiometry, right? So when I give you an initial line, hopefully you can look at this information. Can you tell me which way the reaction has to go? Is it going to go forward or reverse? Which way? Forward. Why? There's nothing on the right side. Yeah, that is correct. Yes, there's nothing on the right side. It can't go in reverse. So that means we have to go in the forward direction. So if we go in the forward direction, we're actually consuming A. So we're going to consume some X amount of A. I don't know how much yet, so I'm just going to call it X. I also consume B, but how much B do I consume? Do I also consume X amount? No, look at the stoichiometry. I actually consume 2X amount of B, and it's because of the stoichiometry. All right, what about the products? I gain 2X amount of D, and I gain 3X amount of E. Does this look familiar a little bit, you know, from stoichiometry stuff, BCA tables, all right? And then we just fill in our columns. Right, fill in our column. So this means at equilibrium, I'm going to have 4 minus X amount of A. I'm going to have 3 minus 2X amount of B. I'm going to have 2X amount of D. I'm going to have 3X amount of E. Okay. So what's the saying I want you to go to bed tonight and say? The E line goes into K. But first we need a K expression. So let's get a K expression from that balanced chemical equation. Products over reactants, make sure to keep track of those coefficients. So K for this reaction is going to be D concentration at equilibrium squared times E concentration at equilibrium cubed over A concentration over B concentration squared. And this is what I mean, the E line goes into K. All of these equilibriums that I have in parentheses, that's what goes into your K expression for the appropriate substance. So we can expand this K expression to, okay, D concentration is 2X squared, E concentration is 3X cubed, A is 4 minus X, B is 3 minus 2X squared. All right, and if I told you what K was, if I told you K was like 25, right? Could you solve that? Technically, yes, you could. You could. There's only one variable. You could solve that. All right, but this has no solution. All right, I didn't give you K, but if I did give you K, you could in fact solve what X was. All right, so that's what we're doing here. Okay, so strategy for ice tables. You need the balanced equation, okay, this one, because you need to know that balanced equation for the change line. The next step is figure out the known values in your ice table. Depending on what's given in the problem, fill in what parts you do know about the ice table. And what will happen is little parts will, you'll be able to calculate other parts of the ice table if you know some parts. It's kind of like playing Sudoku. And I'll show you an example. And then the K expression, where the E line always goes into K. So let's do an example. I try to make this as simple as possible. So if you drink my Kool-Aid for ice tables, you'll recognize that there are 2 different kinds of ice tables that I can ask you to calculate. There's 2 kinds. The first kind is what I call the Sudoku method, where I give you parts of the ice table and you have enough information to fill in the rest. And so in this example, this is what I call question type 1. I give you an initial concentration and a final concentration, and I ask you to calculate K, because K contains equilibrium concentrations. All right, so let's look at this example. So I have a system that contains H2 and I2, and it reaches equilibrium. I tell you that at equilibrium, HI equals that. Calculate Kc for this reaction. So I need to make sure I know all of the equilibrium concentrations to calculate Kc. If I know all the values in this line, I can just plug it into K and then get my answer. But the problem is I don't give you the equilibrium concentrations of everything. I only give you one. So let's just plug in the numbers that we know and see if some patterns come out. So 1 molarity H2, 2 molarity HI. What line will those values go in? think about how the question's written. Are those concentrations at equilibrium? Are they changing? Are they initial? They're initial. Those are the initial concentrations. So we start with 1 molarity H2. So 1 molarity, and I2 is 2.00 molarity. How much HI do I have? 0. Yeah. Don't read into it. I didn't give it to you, so you don't have any. Okay. So for funsies again, which way does the reaction have to go? It has to go forward. You only have reactants. It can only go forward. So I'm going to lose X amount of H2. I'm going to lose X amount of I2, but how much HI do I gain? 2X. Yeah, so plus 2X. Okay, so this is my favorite part where I just add up the columns. So at equilibrium, I'm going to have 1 molarity minus X of H2. I'm going to have 2 molarity minus X of I2, and I'm going to have 2X amount of HI. And so the idea here is I want to figure out what K is. So I need to know HI concentration squared. And of course, all of this is at equilibrium over H2 concentration over I2 concentration. So I need to figure out what these values are, and I can plug them into my K expression. So I could do that. I could just put these like, incomplete expressions into there. But what's the last piece of information I didn't use yet? This 1.87. Where does that 1.87 value go? In which line? The equilibrium line, but which one? That. So I basically told you that 2X equals 1.87 molarity. So now I know what X is. X is equal to, okay, I can do this in my, no, I can't. 0.9. 9. Of course, I didn't write it. Okay, divided by 2. Okay, 935 molarity. Okay, great. So based upon this, all right, I know what X is. I know what X is, so I can just plug in that X to all the other X's that are in the equilibrium line, and I can then plug in those values into our KC expression. So we should see, okay, the concentration of HI is 1 minus X, so 0.065. So that's the actual number. And then I2 will be 1.065. All right. And so these are the 3 numbers that we're going to plug into KC. That's H2, there is I2, and then this is HI. So don't put an X in this value. All right. Remember, HI is equal to 2X. So that full value right there. Right. And now we have all the pieces of information we need to calculate K. So K or KC is equal to 1.87 squared over H2, so 0.065 times 1.065. And so I think it equals something like 51. All right. So can you see why I call this the Sudoku method? It's where you're given like parts of the ice table and you're given like a hint. You're given a hint, and then through that hint, you can figure out what the rest of the table is. You see that? Because if we were not given this piece of information that HI was 1.87 molarity at equilibrium, we would not be able to solve this. It would be unsolvable, right? But it's just through that one little hint, we were able to fill in the rest of the table. Okay, so that's what I call ice table question number 1, the Sudoku method. Here's example number 2, the second question type, where I give you initial concentrations and I give you K. And I ask you to calculate equilibrium concentrations. And if you read that question 2, the second type of ice table may require the quadratic. But in this class, on the exam, there's always an approximation you can use to approximate the answer, and it'll always be close enough. But you need to know how to make the approximation. And I'll show you. right? So technically you never have to do the approximation on an exam. You might on homework or something, all right, do the full quadratic, but you never will on an exam because I'm trying to assess you on concepts, not how well you can do the quadratic formula. To be honest, I have not done the quadratic formula in a long time. I plug everything into Wolfram Alpha to solve for me, or I use the approximation. Sometimes I just do the full quadratic on Wolfram Alpha. I do the approximation to check, okay, does my approximation give me the same answer as doing the quadratic? And usually it does. Usually I get it within like 1% of the answer, all right? And so I'll show you those examples. So let's do this ICE table. It's still the same strategy. Plug in what you can, all right? And we'll figure out, you know, how to solve for it. So here's our initial conditions. AD is 0.1 molarity, so 0.100 molarity. There, okay. Which way does the reaction have to go? To the product side. So we're going to do minus X plus X plus X. Everything's just a one to one, so that's nice. So that means at equilibrium, I'm going to have 0.1 minus X of AD. I'm going to have X amount of A and X amount of D. If I, you know, set up my K expression, which I give you, is 3 times 10 to the negative 10, is equal to A concentration times D concentration over AD concentration. Okay, so what is the trick with ICE tables? The E line always goes into the K expression. So let's do that. All of these concentrations we got in our E line now go into our K expression. So we can say that X squared over 0.1 minus X equals K, 3 times 10 to the negative 10. Can we solve that? Can we solve that? Yeah, we can, but it requires a quadratic and that's annoying, all right? So that's why I have that up here. I will give you the quadratic formula on the exam, all right? Let me propose an approximation we can make. Okay, let's look at the value of K. Okay, K is real small. So what do we have a lot of at equilibrium? Product or reactant? Reactant. So based upon this ICE table, right, we initially start with all reactant. Is the reaction going to go forward that much? If K is really small, K is really small, and I say at equilibrium, you have a lot of this present, is X going to be a big number or a small number? It's going to be really small, that the reaction isn't going to go forward that much. So if X is really small, all right, compared to the 0.1 concentration that I started of that reactant, the approximation I'm going to use is that this minus X on my reactant concentration is negligible, and I can just get rid of it. All right, and I'll show you that it's true. Right? So when we have our K expression here, we can actually simplify it to X squared over 0.1 equals 3 times 10 to the negative 10. Does that require, what's in blue? What's in blue? Does that require a quadratic? No, it's just like a square root that you have to do. Which one do you want to do? Do you want to do the green one or do you want to do the blue one? You want to do the blue one, right? Where you just have to take a square root of a number. So the approximation that I went to go from green to blue is I just said, oh, this minus X is going to be super small. So I'm just going to get rid of it to really simplify my answer. All right. And so if you do that, all right, if you do that approximation, you will get X is basically the same number for both of them. And I'll show it to you, right? Note about the quadratic formula. So here's, I think, the same thing. Those are the two. This one requires the quadratic. This one uses the approximation. I put both of them into Wolfram Alpha. Here are the answers for the first one, right? Those are the answers for the first one. So first off, which X do I care about? The first one or the second one? The second one. Why the second one? The first one's negative, all right? So that's our answer, all right? That's the full quadratic. You solve the whole thing. Here is the approximation. See how the approximation is missing that minus X on the denominator? So if I put that into my trusty Wolfram Alpha, look at my answer. 5.4777 2, 3. So it's different in the fifth sig fig. It's different in the fifth sig fig. To me, those are the same answer. Do you agree that they're basically the same answer? But think about what X is, right? You just calculated that X is literally a number with point and then 5 zeros in it. Is that going to change that value in the denominator? No, look at the number. It's 0.100 and then you minus X. If you actually do that operation minus X, your answer in the denominator is going to be like 0.09999. Like you didn't change it that much. And that's why the approximation works. And it works for K values that are really, really small, where we know that our reaction remains primarily on the reactant side, right? So on exams, you will always be able to use an approximation. I'm not going to tell you which one. All right, so which one do you want to do? Quadratic or approximation? Approximation, yeah, it's a lot easier. And we essentially get the same answer. All right, so we got X, all right? That X is equal to, is that my answer? Yeah, is my answer a little bit off? It is a little bit off, okay, in the corner there. All right, so it's 5 point, what did I just say? 5.5 times 10 to the negative 6. That is what X is. But what you need to check, all right, don't just go putting that in the answer box on online homework or on the exam. Look back. What does the question actually ask? What is the concentration of A at equilibrium? So is X my answer to that? And how do we know? What is A at equilibrium? It is X. Yes, so this is my answer. This is my answer, A at equilibrium. Because if I asked you what is AD at equilibrium, then you would have to do this like that calculation first or something. Good. All right. So that's as hard as things go. You know, the math guy, some math engineer person asked me, you know, what's like the hardest math that you do in 1250? And I told him this was the hardest thing. And so, because they wanted to make sure that you were ready for this class, but I don't think this class requires anything more than basic algebra. Okay. Want to do another one? All right. Maybe I'll ask for your feedback. What is the hardest math stuff in this course? So I can help the math folks do their course. Like it's like the pre-engineer math thing before you get into like the calc series. So people who like need extra help. I don't know. Okay. Anyway, so let's do another ice table. So this is type 2. So may require the quadratic. May. So I give you initial concentrations, or no, these are pressures. So we're going to use Kp for this, but no problem. We just need to make sure our junk is in the right place. So in our ice table, we're going to have 0.5 atm of A2 and 0.5 atm of B2. How much AB do I have? 0. Yay. So which way does our reaction have to go? Backwards. Yes, because I have no reactant. So I'm going to subtract X amounts of A and B, and I'm going to gain how much reactant? 2X. Yes, do not forget that 2X or you will be very sad. All right, let's fill in our table. So 2X of AB at equilibrium, we have 0.5 minus X of A2, and I have the same 0.5 minus X of B2. All right, so I give you K, but it's Kp. So P stands for what? Pressures. Everything's in pressure. So it's still operated the same. We're just going to work in pressures instead. So we don't have to change any of these values. It's just understand we're in pressures. So K is pressure of A, pressure of B2, sorry, and then pressure of AB, but it has to be squared. All right, what's the trick with ice tables? The equilibrium line always goes into K. So all of this nice stuff that we just got goes into K. So let's put those in there. So K, which is equal to 100, I told you that, is equal to 0.5 minus X times 0.5 minus X, or the numerator is just squared. Great. Over 2X, that whole thing is squared. All right. Do you want to do a quadratic? You want to? No, I'd prefer not to. I would like to go the rest of my life without doing the quadratic. Is there any math trick we can do to simplify this? Is what? Square root the whole thing, both sides. If we square root the whole, both sides, boop, boop, don't we simplify the right-hand side? It becomes, what's 100, the 10? Sure, okay. 0.5 minus x over 2x. Does that require a quadratic? No, that just requires arithmetic to just move stuff around and solve for x. Great. Right, so this actually doesn't require a quadratic. It just requires a little bit of math know-how to recognize that once you set up the k expression, it's a perfect square because you have a squared species on both the top and the bottom, right? And so, yeah, you can solve for that. So x, when you get it, all right, when you solve for it, x is equal to 0.0238 ATM. All right, is that my answer? Not necessarily. This is actually asking calculate all of the equilibrium concentrations. So what I actually have to do is plug that x back into the equilibrium line to get all of those concentrations at equilibrium. And this is as hard as this class gets, or I guess in terms of ice tables, this is the hardest that it gets, right? And so plugging those values in, recognizing x is just because I solve for x, it's not necessarily my answer. I want equilibrium concentrations. So AB is going to have a concentration of 0.047 ATM, all right? And then A and B are both gonna have, 0.5 minus X. So both of these have a concentration of 0.476 ATM, all right? Okay. So now with that answer, is there a way we could check our answer? Does check that our equilibrium concentrations are right? How could we check our answer? Yeah, plug it back into K. If we plug all of these concentrations we just got back into K, we should get 100. And so if you take this number, square it, divide it by that number, you should get 100, hopefully. Okay, and that's how you can check your answer. Because those are equilibrium concentrations, we can plug them back into K. All right, so that is as hard as this class gets. Actually, I think Chem is pretty hard too. Right, not that bad. You never technically have to do the quadratic formula as long as you know the approximation that you can make. All right, so what the quadratic formula? But the thing is like, okay, so like if you have this, right? Okay, and you want to do the quadratic formula, you have to move things around. Don't you have to move things around to get it into the A, B, C form thing? And I'll probably mess up. So that's just me. But yeah, there's most instances there is an approximation you can make. Okay. Or if you want to just solve the quadratic, that's fine. You'll get the same answer. All right. Okay. So that is ice tables and chemical equilibria. We talked about Le Chatelier's principle, which is we start at equilibrium. All right, we start at equilibrium. So that essentially is our I line. We make some type of change, all right, and the reaction has to shift itself to get back to equilibrium. That is what Le Chatelier's principle is. And we use the seesaw analogy just to kind of give us a relative idea of which way the reaction goes. But really, because Le Chatelier's principle, why we have a disruption in chemical equilibria is because we're disrupting the forward and reverse rates. I showed a picture here, right, where if we add H2 gas initially at equilibrium, this reaction's at equilibrium, I'm adding a reactant. Our intuition says that the reaction goes to the product side, but the reason it goes to the product side is because since we're increasing H2 concentration initially, we actually increase the forward rate of the reaction. So it outcompetes the reverse rate. And that's why the reaction shifts to the product side. All right, so that's Le Chatelier's principle. So those hopefully should be low-lying fruit for the the final exam, because it's no calculations. Okay, all right. So we're gonna skip over all of that. So we have 20 minutes. I want to talk about another type of chemical equilibria, and I think it's easier. I like this part of the chapter because, oh yeah, so I skipped. So we already did chemical equilibria. So I am on slide 32. So we're going to talk about solubility equilibria. So it's still K, but it's to a specific type of process, and it's called solubility product. We're going to look at why some solids dissolve in water and why some do not. So you remember in chapter 3, do you remember this table? Do you remember that? Does that give back memories? All right. Well, how did we use this table? If I told you like NaCl, you would use this table to predict whether this was a solid or aqueous in a chemical reaction. Is NaCl solid or aqueous in a double displacement reaction? It's aqueous because it is an N plus, all right? Okay, and it's chloride containing, and it's not one of the exceptions, all right, that it's aqueous. So the question is, okay, well, why was that soluble? Versus if we had something like, magnesium hydroxide, right, in a double displacement reaction, why did I make that soluble or a solid? Okay, in a double displacement reaction, why is magnesium hydroxide solid while NaCl is aqueous? It all has to do with chemical equilibria. Chemical equilibria related to the chemical equilibrium created by the ions that are dissolved in solution when you have a saturated solution. So I don't think, no, yeah, we didn't do this reaction in lab. Don't like to use lead, but in this double displacement reaction, if we took lead nitrate and sodium chloride and we mixed them together, we would get this beautiful yellow solid come out. That's the reason why school buses are yellow, right? It's because of the lead iodide in the paint of buses to make it this beautiful bright yellow color. And so that solid is formed between lead and some halide ion. But the thing is just because you make a solid, right, doesn't mean that there's some small amount of ions in solution. And that's what this saturated solution is being dictated by, all right, the saturated, right? That if I had lead chloride solid and I put that in water, we would see that chunk fall to the bottom of the beaker, but a small amount of those solid particles will be dissolved in the solution, a very, very small amount. Do you notice what kind of arrow this is? Equilibrium. So that means that we can actually write a K expression to describe this, that every solid has a K expression, specifically KSP, to describe the solubility of solids. So this is why, all of these substances are really soluble. They have really large KSP values, while the substances down here, the insoluble stuff, they have really small KSPs. So their stuff doesn't dissolve that well. All right, so let's do an example. All right, so the KSP is just a specific K expression for the solubility of a solid in contact with its saturated solution. So here's an example. If I have barium sulfate, right, barium sulfate solid, and I put a little bit of it in water, right? So here's my barium sulfate. I put a little bit in water. Some of those barium 2+ cations separate from the sulfate anions. Some of it dissolves, all right? That's what you see here. You see how we have the free cations and anions all broke apart. It's dissolving. This is aqueous, right? I keep, and so that's what you see here, all right? This is barium sulfate aqueous. So I put a little bit of barium sulfate in. What if I add like a huge amount of barium sulfate in there, right? Some of the solid will dissolve to a point where there's no more barium sulfate can go into solution. That's what this last picture is showing. See that big chunk of solid at the bottom? There's our solid, but see how it's surrounded by this aqueous stuff around it. So a saturated solution is when we have solid stuff that's undissolved in contact with its ions around it. That is a saturated solution. So this process is actually a chemical equilibrium. All right. So this is the reaction that's happening in our saturated solution. Saturated. Right. We have barium solid. See, it's down here. And it's in contact with a certain concentration of barium 2+ and sulfate ions around it. So we can write the K expression for this. Specifically, it's KSP. SP stands for solubility product. Just understand it means a solid dissolving in water. That's what it means. It's just a special kind of K, but it's no different than any other K expression that we've done. So K for this reaction is going to be barium 2+ times sulfate 2- concentration. That's it. So KSP is inherently easier because in a KSP expression, the reactant is always a solid. So will that ever show up in your K expression, your KSP expression? No, we don't put solids, we don't put liquids in our K expressions. And that's the same thing goes for KSP as well. All right, so I want to get through these so we can do our demo. Okay, KSP and ice tables. Again, these ones are easier because KSP, the expression never has anything in the denominator. So it's going to be just generally an easier calculation to do. All right, so if I tell you that the concentration of a saturated lead iodide solution is that, what is the molar solubility of lead iodide? So the idea here is I want to, hold on, calculate this. Oh yeah, this is the molar solubility of lead iodide. Yes, so when I put lead iodide solid into solution, the solution around it, all right, this is my lead 2+ concentration, my iodide minus concentration. If I measure the concentration around this, I should record a concentration of this value. But I'm asking what is the KSP value for this reaction. So I'll show you how to set up these ice tables, and it's specific for KSP reactions. All right, so here's the strategy. Here's the KSP for the dissolution of lead iodide. We start with the solid, we get lead 2+, we get I-. So how I approach this ice table, I'm going to start with some random amount of solid. I don't care how much I start with because that number is never going to go into the K expression. Do you agree with me? Like, because it's a solid, it doesn't go in it. So I'm just going to call it N. All right. And I'm going to start with 0 of my ions. All right. So which way does this reaction have to go? It has to go forward. Yes, because I start with solid, I have no reactants. So I'm going to lose X amount of my solid. I'm going to gain X amount of my lead 2+, and I'm going to gain 2X of my I-. So at equilibrium, I'm going to have N minus X of the solid and have X of lead 2+, and I'm going to have 2X of I-. Great. So I'll point out what molar solubility is. This X value right there, the amount of solid we lost, this is molar solubility. Solubility, all right? That's molar solubility. So we are given what that is. We are given that that is equal to 0.001713. This is X. All right, it's how much solid you lose, how much actually goes into the solution. And so that's great because we know what X is. I can plug that value, all right, into my E line. And then the trick with ice tables is that the E line always goes into the KSP expression. So let's get that. KSP equals lead 2+ times I-, but squared. And so we want to put our E line into our KSP expression. So KSP, and that's what we're solving for, is equal to X times 2X squared. And if we simplify that further, that becomes 4X cubed. And so now let's use that little piece of information, the little hint that was given in the question, and that is the molar solubility. That is X. So if you plug that in, you get the value of KSP is 6.43 times 10 to the -9. So based upon that K value, remember, this is no different than the Ks we talked about earlier. KSP is really small. So is lead iodide very soluble in water? No, because K is a real small number. You're not going to make that many ions. You're not going to make any. Most of it's going to stay on the product side, or sorry, the reactant side. So this is why they paint school buses and the like lines on the road with lead iodide based paints, because you might be thinking, well, lead, like they've ruled out, or they've made it like illegal to use lead paints in today's like society. But that's like for homeowners. Homeowners can't use lead-based paints, but they still use lead-based paints on school buses, on roads, because their safety, how bright they are, outweighs the, I guess, health effects of having lead 2+ in the waterways. And also what we see here is that the dissolution of lead 2+ and I- is really, really, really small. So if you have a full school bus and you paint it with lead iodide, not that many, because KSP is so small, there's not that much lead 2+ that goes, that gets dissolved. But I would still not recommend like licking a school bus or licking the yellow lines on the road, right? Just because KSP is really small. I'm just saying that, you know, you need to kind of weigh health risks and reward in this case. And the reward is yellow paint is really, really bright for things to keep children safe and people on the correct side of the road. And so that's what, you know, you should be weighing those options here. Okay. All right, so the school buses. Okay. All right, let's do another kind of ice table calculation. This one's similar to a type 2 ice table, but there's never a quadratic necessary. So here, so in this question, I asked you to calculate KSP, and I gave you what X is. So I guess think about how's the other way I could ask you it. If I give you KSP and I ask you to calculate X. So that's what this next one is. Let's calculate the molar solubility of barium sulfate if I give you that KSP. The setup is the exact same. Start with the KSP expression for barium sulfate. So we take barium sulfate, we split it up into its ions, start with some random amount of barium sulfate. I like to just say an N amount. The reaction has to move forward. So minus X plus X plus X. And so at equilibrium, we have N minus X of the solid, X amount of barium, and X amount of sulfate. So what we are calculating is molar solubility. That is X, this value, minus X. This is molar solubility. That's what we're solving for. So we can use the KSP expression to help us solve for X. So just because we're solving for this minus X term, right, how much barium sulfate we lose, we see that X propagate itself in the concentration of species on the other side. So just because we're not measuring this minus X directly, we can get it from the concentrations of junk that actually do go into solution. So KSP is equal to both of the products. So barium 2+ times sulfate 2-. So KSP is just equal to X squared. Do you agree with me? Because what's the trick? The E line goes into the K expression, right? And so since we're given K, X squared is equal to 1.1 times 10 to the negative 10. And so we can get X. X is just equal to that number, all right? 1.1 times 10 to the negative 5. That is X. This is our molar solubility, okay? So what this tells me is that 1.1 times 10 to the negative 5 moles of barium sulfate will dissolve in 1 liter of solution. That's what it's telling me, right? 1.1 times 10 to the negative 5 moles, that's real small, but I don't really know what a mole is. Like I can't just like look at a sample of barium sulfate and be like, yeah, that's a mole's worth. So it might be easier to report this in gram amounts instead. So we haven't done one of these calculations in a long time. How many grams of barium sulfate can be dissolved in 1 liter of solution? So we already got the molar solubility. 1.1 times 10 to the negative 5 moles of barium sulfate can dissolve in 1 liter of solution. So to get this into grams of barium sulfate, we just have to use the molar mass. So I give you the molar mass right there because you guys are older and wiser, and I assume that you know how to do it. All right, so where am I going to put the 233.38? Am I going to put it on the top or the bottom? Top or bottom? Do you remember how to do this? Bottom? Okay, I thought you said bottom. Yes, on top. Yes. Okay. All right. 233, 38 grams, 1 mole on the bottom. And so then we calculate a gram amount per liter. And that might be more useful for us to understand like how much that weighs in lab. But we see that amount is still really heckin' small. Okay. 2.4 times 10 to the negative 3 grams per milliliter. That's 2.4 milligrams per liter. All right. Half of you have already had your last lab day. Aw. All right. In chemistry here. So remember using the analytical balances and think about how much it took to get the number to just change in the 3rd decimal place. It's like almost nothing. It's like just sneezing on it and the number changes. So not a lot of barium sulfate goes into solution. That's basically the moral of the story. And that's in a liter's worth of solution. Actually, no, a liter is not that much, like this much. Right, you're gonna just get a speck of it to dissolve. All right, I wanna actually do the demo. So we'll come back to that one. We'll do the demo. Okay, we can actually disrupt saturated solutions. Okay, so I have a demo here. All right, I have 2 things. Which one do you wanna do first? Let's do NaCl first. Okay, so I have here a saturated solution of NaCl. So I have it right here. All right, it doesn't quite look saturated, but it is. I just had, oh no, you can see a little bit of solid at the bottom, but the team, they filtered it right before bringing it to me. All right, so there's my solution of saturated NaCl. So I'm gonna disrupt this chemical equilibrium. It's already at equilibrium, it's already saturated. I'm gonna add HCl to it. All right, HCl. So like, look at the equation. We have NaCl solid, Na plus, Cl minus. What happens when I add HCl? Think Le Chatelier. What am I adding if I add HCl? I'm adding chloride. So which way should the reaction shift? To the reactant side. So what should we observe? Solid. Let's see if it happens. Don't blink. Yes. Oh God, it smells. Okay. Yep. There we go. Did solid form? Yes, it did. All right. And so, ooh, there's conc acid on the table there. Okay. So yes, solid form. All right. So that was us disrupting the equilibrium of a saturated NaCl solution. So I have another saturated solution. This time it's magnesium hydroxide. So it's the second one there. Okay. So for this one, what I want you to look at is the equilibrium here for magnesium hydroxide. All right, I have magnesium hydroxide solid. So you see the solid, like we already see the solid, right? And we see there are some Mg2 plus in solution and hydroxide in solution. I'm gonna add HCl again. We're disrupting the equilibrium, but a little bit differently. How can HCl interact with these things? There's no common ion, but HCl is also a acid. What reacts with acids? Bases. Is there a base somewhere here? Yeah, hydroxide. So if I add acid, it's going to react with that hydroxide, essentially removing it. All right, so I'm removing a hydroxide. I'm removing a product. So which way should the reaction shift? To the product side. Yeah, because I'm essentially removing hydroxide. It's like consuming it. So if it shifts to the right, what should we see? The solid should dissolve. Yes, the solid should dissolve because the reaction shifts to the product side. So let's see. What? Okay, yes, thank you. Okay, I think I have to add a lot. Oh, fudge. Dissolve. Oh. Okay, so this is the reason. So if we add acid to things that have bases in the chemical formula, right? Adding acid reacts with hydroxide, shifts the reaction this way. You go onto Pinterest and look at all those crunchy moms who use vinegar and lemon juice to clean everything. they actually are doing something right. Because acid, all right, lemon juice, vinegar, all right, they're highly acidic. What it does is actually disrupt the equilibrium for crud stuck on things and dissolves them. Are we actually seeing it happen? It's happening? It is? Yeah, so it's getting clearer. It's really ugly. Yes, but it's happening. All right, so yeah, that's why, you know, how you like clean your shower head. Have you ever Googled how to do that? They say to soak it in vinegar because you're essentially taking magnesium carbonates. Carbonate's a base. So when you add vinegar and acid, you're disrupting the equilibrium, consuming carbonate, the reaction shifts to the product side. And so all those crunchy moms are doing something right. In terms of disrupting KSP, those things do not do anything for like disinfecting things. All right, so there you go. That's why you use lemon juice and stuff to clean stuff. Okay. Is it happening? It's going. Oh, that was scary. I thought it was gonna boil over.